Hello everybody, my name is Josep Manguez. I'm jointly with Jose Nunez, my colleague from the IP Technologies area and other colleagues of the IP Technologies area of the CTTC. We are presenting you the demo that we prepared for the project Femto, which is a European project that just finished. And in particular, this contribution is about a proof of concept, so it's a real testbed that we deployed here at CTTC on routing and load balancing in what we call a network of Femtocells. We have other videos in our wiki where we explain what a network of Femtocells is, but to briefly summarize the idea, the basic idea is to provide flexible mechanisms so that you, for example, in a stadium, in a large corporation, or even small ones, or in temporary deployments like conference halls, you can quickly and easily deploy Femtocells. And we also, in the project, we also define entities both at the mobile network layer and at the transport network layer to confine the traffic as locally as possible inside the network of Femtocells, so that you can access, for example, local services in the network of Femtocells without going to the core necessarily. So we have defined all these entities, and what we are presenting here is mainly an improvement of the transport network layer, specifically designed for exploiting as much as possible the wireless resources, because in our case we have all wireless networks of Femtocells, meaning that we form a mesh of networks of Femtocells, and they are wirelessly interconnected in the form of a multi-hub wireless network inside the company or the stadium or wherever we deploy that. So let's proceed with the demo, but before going to the demo, let us introduce a bit the main concepts of what we are showing in this demo. So again, we also have other videos in our wiki explaining the main ideas, but to briefly summarize, this slide gives you the main ideas behind our scheme. So in our routing scheme, we don't build routes as in conventional routing protocols used in multi-hop wireless networks, but we take decisions on a per packet basis, only based on the local information exchanged between one node and its neighbors. So the big idea when we take routing decisions is to gather information from the queueback logs of neighboring nodes, and this is the delta Q parameter that you see in the weight that we calculate for each link. And this delta Q is the Q differential between the queueback log of the local node taking the routing decision and that of each of the neighboring nodes. So we have such a delta to build a different weight for each of the links. So this is the, let's say, back pressure component of our routing scheme. And then we have a second component, which is the function PIJD, which basically provides the geographic component. So in this case, and you have the definition of how, in this case, in this specific proof of concept, we define this penalty function, P comes from penalty, which tends to, let's say, prioritize paths that towards neighbors that allow a certain packet to reach the destination through the shortest path. And when we combine both this back pressure component and the other geographic component in the form of this P function, we weight both parameters through this V parameter that we have next to function P. And this V parameter is very important, as you will see in the real-time demo that Jose will show you afterwards, because by appropriately weighting this parameter, and this is what is illustrated in the figures below, so what these figures below represent are is a 10 by 10 wireless mesh network of femtocells, and this is for a low V parameter, which means that we mainly take decisions based on Q-backlog and the congestion of the nodes. So this basically means that we try to distribute as much as we can the resource consumption. This means wireless resource consumption, the Q backlog, or it could be any other parameter. But the main idea is that we distribute the resource consumption. As we increase the value of V, like in this case, or in a more extreme case, what we see is that we mainly take decisions based on getting as fast as possible, let's say, through the shortest path towards the intended destination. That's the basic idea. So our goal, as you will see, and this is what is explained in the lower part of the slide, our goal will be to adapt this V parameter depending on the network conditions, which mean traffic load or the congestion of the nodes or these kind of things. And we do that, as I explained before, on a per packet basis. So for taking and modifying this dynamically modifying this V parameter, we take into account not only the absolute value of the Q backlog of the nodes, but also the rate at which the Q backlog increases. And based on that, we modify the value of V for taking the decision for the next parameter, for the next period. And the other important thing is that we do it on a per packet basis in the sense that we also take into account other parameters of quality of service, if you want, of the packet. In this case, for this specific proof of concept, is the TTL that we are using. So if the TTL goes below a certain threshold, then we increase the value of V so that for this specific packet, but only for this specific packet, we go through the shortest path and as fast as possible to the destination. Otherwise, it will consume resources, and in the end, this packet will be discarded. In other implementations of our scheme, we could use any other DSCP value in the header or some other definition of flow that you may want. So this is the basic idea of our routing protocol. And what is the setup that we deployed for bFemto? So this is the plan of the first floor of the CTTC building in Barcelona. And the basic idea is that we deployed 12 nodes consisting of each of them of what we could call a wireless home node B, where we have a femtocell, a commercial femtocell, a 3G commercial femtocell in this case, because at the time we started the project, there were no LTE femtocells, so the proof of concept is with 3G flows, though the architectural ruling in bFemto is more on EPS. But in this case, the basic ideas are the same, so it would be applied to an EPS system without problems. So the basic idea, as I said, is that we have 12 such nodes, and in this case, for the demo that you will see, we have deployed 3 UEs, 3 user equipment with its corresponding card, conventional ones, that will attach to 3 of these other nodes. So this is one UE that will attach to this femtocell. This is another UE that will attach to this other femtocell. In this case, these 2 femtocells are in the room that we are recording the video, and then we have another one in the first floor of the CTTC, but the scheme is still the same. So in our demos, in all the demos that you will see, the flows will be generated by these 3 nodes. And all the rest, so the traffic in the end will go this way. So the UE will generate a 3GPP flow, then through a regular UU interface, you will reach the wireless home node B, and then through 5 GHz Wi-Fi multi-hop, we will reach what we call the local femto gateway. The local femto gateway is an entity defined by bFemto that deals both with the mobile network layer, so as to try to confine the 3GPP procedures to the network of femtocells, but also in our case, it's our aggregation point of the traffic generated in the old wireless network of femtocells, because from the local femto gateway, then through the IUH interface, we reach the core emulator that we have in our lab, in what we call the extreme testbed, in the second floor of our building, and then the external node, which is emulating the internet. And all these, and what we have in the lower part of the slide, as I said, all this is controlled by the extreme control network through which we synchronize machines, we execute the experiments to generate the flows, and so on. We have another video in the wiki describing how the extreme testbed works, if you're interested. So, in terms of testbed, let me give you a bit more detail of what is a wireless home node B. So, in this slide, what you have is a picture of one such wireless home node B, composed by a commercial femtocell, in this case a Sagemcom femtocell. And then what you see below the femtocell is a small form factor PC where the logic of our routing protocol works. So it's a Linux machine where we put this, the logic of our routing protocol. In the figure, you all see that we could build multiple radios, though for this proof of concept, we are just using one for the backhaul. And in terms of protocol stack, it's a regular IUH stack. So the leftmost part, this part over here, is the protocol stack of the conventional, the 3G femtocell, the commercial 3G femtocell, offering a UU interface towards the UE. And then this is our wireless mesh router, which is the one in charge of handling all the traffic coming from the femtocell in the multi-hop wireless network of femtocells. The important thing here is that we put our logic here. And how did we put that? The interesting thing is that we reused the code, exactly the same code that we developed for our simulations in NS3. And we did that through the NS3 emulation framework. Of course, for the specificities of our protocol, we need to take into account the QBAC log of the buffers of the real device. So there's some sort of communication. But the logic of the protocol, which is implemented in the NS3 IP stack part, is exactly the same as in our simulations. And this specific part of the routing scheme did not need any modification. So let's move now to the evaluation. So after this introduction, let's first start by generating a single flow to show you how, what are the implications of fixing V or putting a variable V. So in this case, in the first experiment, one of the UEs that we have in the room where we are recording this video, we generate a flow, let's say in the uplink direction towards the local femto gateway, and after that to the external node, which is in the top right part of the slide. But we're focusing here to show you how things evolved in the old wireless network of femtocells. So this flow will go straight to the local femto gateway because in this specific experiment we have a fixed value of V. So we are not modifying depending on the conditions of the network. It's a fixed value of V and a high value of V, meaning that we are interested in reaching the destination through the shortest path. So based on our geographic information, we'll go straight to the destination. And this is what Jose will show you now real time.
This is the graphic user interface that we developed within the context of the bFemto project. As we can see here, we have the network parameters, the network performance metric that are able to measure the performance of this old wireless network of femtocells. And here we can see a representation of the first floor of the CTTC building resulting from the deployment of a 12-node all-wireless network of femtocells that we deploy within the context of the Femto project. In this case, we are showing experiment, a real-life experiment, in which one flow is sent from this home node B to the local femto gateway, which is the node in the top left border of this close-to-grid topology. These real experiments are relative to the current experiment that we are running. This means that the color depicted by these nodes is relative to all the colors within the same experiment. On the other hand, what's happening in this experiment? As Josep explained, we configure the B parameter of the routing protocol with a very high and fixed value. This means that routing decisions are merely taken using geographic information, and so just Euclidean distance to the local femto gateway is used to forward packets. And this is the result of the experiment, which means all the packets use one single path to reach the local femto gateway.
Okay, thanks, Jose. So the basic idea now is, in this new experiment, we are maintaining still the same value of V, which is high and fixed. And now we'll see how the protocol evolves when there is some impairment in the network. For example, a node goes down, which is the node with marked with an X. And what will happen, what you will see real time, but I'm explaining a bit before Jose shows you the operation in real time, is what you will see is that every 20 seconds we are switching on and off this node. And what we are presenting here is the evolution that you will see over time. Off, in this case, the queue overflows. So if you focus on the red curve, what you see is that when the node is switched off, all the packets that we are sending are lost, because the only neighbor that can help us reach the destination is down. So then we cannot send these packets to our preferred neighbor, and then all of them are lost. So when the node comes on again, then there are no losses, and then there are losses, all the packets are lost, and so on. And this is what you will see in the heat map now.
In this experiment, we are periodically switching on and off this home node B. The routing protocol is still configured with a high and fixed B parameter, which means that we merely use geographic information to reach the intended destination, which is the local femto gateway. As we can see here, we are plotting the queue backlogs in the network of femtocells, and when the node is switched off, we can see how the queue of this node is full. Once the node is switched on again, we can see how the queue backlogs is able to practically decrease its congestion, and so just a queue backlog of 2 packets is on the source, home node B. Another time we switch off this home node B, and the queue backlog of the source home node B gets full, leading to queue overflows in the network of femtocells. Once the node is switched on again, all the packets are able to reach the destination, as in the previous case. But as we will see in a few seconds, once the node is switched off, there are no packet transmissions with the current configuration of the routing protocol. In the next experiment, we will see how a variable V algorithm is able to not lose any packet, as in this case, when the nodes are either switched on, when this node is able to switch on or switch off.
Okay, let's now move to our ideal case, let's say, the reason that for which we designed our variable V scheme. So based on the observations that you have just seen, we decided to go for a variable V scheme that adapted to the network conditions. So now we are running experiment on a variable V scheme, still with one flow, the same flow as before. So nothing happens when all the nodes are up, so we still take decisions for going straight to the destination, but the crucial difference here is that when the same node as before goes down, the V parameter is adapted, in fact is lowered, so that the decisions are not taken anymore only based or exclusively based on reaching the destination as fast as we can, but on balancing the congestion of the nodes. So what happens is that when this node goes down, this other node will start increasing its Q-backlog. So the Q-backlog differential between this node and this other node will grow. And then this will be the parameter determining our routing decision. So the packet will be diverted to this other node, and then in this way we can circumvent the hole. So before going on and showing you the real demo with the real-time heat map, let me explain again, based on these graphs that show the evolution over time, what is happening. So in terms of Q overflows, red curves is still the same. It's for the previous case, so the fixed V and high value of V, so packets were lost when the node was going down. But in this case, what we see is the green curve, so no Q overflows at all. So we are not losing any packet. In terms of what happens with the V parameter over time, what you see is that every time, again, we are switching on and off the node every 20 seconds. So when the node goes off, so when the node is switched off, the V parameter is decreased. But when the node is switched on again, then the V parameter is increased. So we take destinations through the we take routing decisions still based on geographic proximity to the destination. In this way, we get the best of both worlds, let's say, of back pressure and geographic information. And just a specific snapshot in terms of time, evolution over time of packets transmitted. So what you see in the red curve still represents the fixed value of V, is that when you switch off the node, packets are lost, so you don't transmit any packet, as Jose showed. And then when the node is switched on again, then you start transmitting packets. On the other hand, in the green curve, what you see is that when the node is switched off, you still transmit packets. You need to wait a bit until the Q-backlog of the congested node increases. And when node is switched on again, we have all these packets in the Q-backlog of the initially congested node that are sent through the shortest path, and that's why you have these peaks of packets transmitted. And then we reach again the more or less stationary state, and so on. And now Jose will show you, let's say, the most interesting part of this demo, because it shows how the variable V scheme works.
This experiment illustrates the result of applying a variable V algorithm for the current network configuration, which, as we previously explained, is based on switching on and off periodically this home node B, which is a key node in the process of routing packets to the intended local femto gateway. You can see here how when the node is switched on, all the packets traverse the shortest path to reach the destination with the variable V algorithm. And as we will see, now when this node will be switched off, which is going to happen in a few seconds, now is the time, and we can see how the variable V algorithm is able to circumvent the hole using a longer path to reach the intended local femto gateway. So the variable V algorithm is able to do what I just previously explained. It's based on the configuration, auto-configuration in each home node B of the V parameter. So when the nodes are switched on, all the V values in the network are static, fixed. But once we switch off this node, whose V value is not modified, these nodes decrease their V values, and so the degree of load balancing in the network. How do the V values are modified in a distributed and self-organized way in the all wireless network of femtocells? We use queue backlogs around the one hop neighborhood to modify the V value. You can see here we need a node with queue of 100 packets in order to circumvent the hole and decrease the V parameter. Once the node is switched on, the queue backlogs of the home node B sending the 3GPP flows decreases to 2 packets, and the V parameter comes back to its previous value, which is a high fixed V value. Once the node is switched off, the V parameter decreases as a consequence of the increase of the queue backlog in this node. And finally, we will see how, in terms of queue overflows, there are null queue overflows in the network in both cases, when the node here is switched on and when the node is switched on.
Okay, now that we have seen that our variable V scheme works with a single flow, let's put more flows in the network. And in this case, all the UEs and femtos that we have deployed for this demo will be like handling traffic. So the UEs that we have in this room where we record this video and the UE that we have in the first floor of the CTTC, all three together and at the same time will send traffic towards this external node, which is after the 3G core network emulator. So we will aggregate all this traffic in this local femto gateway, and of course our scheme will still work, as Jose will show you.
This experiment illustrates the injection of 3 GPP flows, one flow sent from this node, other flow sent from this node, and another flow sent from this node. In this case, we still have one node able to put packets from the network, which is this node. And as we can see here, this is the node with the more number of packets transmitted as a result of that is the only node able to pull packets from the network of femtocells. So this is the more congested region in the all wireless network of femtocells. In the next experiment, we will see how by incrementing the number of local femto gateways around the primary local femto gateway will decrease the congestion in the all wireless network of femtocells to an extent in which the primary local femto gateway will not pull any packet from the network, which is very useful for decreasing the congestion in an all wireless network of femtocells.
Okay, let's now move to a bit more complex case, let's say. Up to now, in this demo, what we have seen is that our scheme allows us to exploit as much as we can and evenly balance the resource consumption in the network, understanding resource consumption in the form of wireless transmissions or memory used for storing packets in the buffers of the nodes. Now let's put an additional resource to help us increase the performance of the network of femtocells. And this additional resource is new local femto gateways. So that these local femto gateways have each a wired connection towards the core network so that they can pull packets and send them through the wired network of the company or of the stadium or whatever to this core network. So in this way, if we pull packets out of the network in what we could call these opportunistic local femto gateways, we consume less wireless resources than before. And the scheme that we generated is exactly the same three flows as before, exactly the same destination as before, but to illustrate how this would work, how these local femto gateways will opportunistically pull packets out of the network, we deployed them in this position that you see just below the previous local femto gateway, the reference one, which is still the reference one, and this other local femto gateway, which is still next to the reference one. So packets, so what you must understand is that packets are still have as destination this external node on the internet, let's say, but through this local reference femto gateway. But since flows will cross opportunistically these local femto gateways, it will be these opportunistic local femto gateways that will pull packets out of the network. In this way, this wireless hub and this other wireless hub will not have packets transmitted, and then we will consume less wireless resources. And this is exactly what Jose will show you next.
So in this case, we are injecting into the network of femtocells the same number of flows, three GPPV flows, as in the previous case, using the same home node Bs as sources. So this one, and this one. As we can see, there are no packets pulled from the network by the primary local femto gateway as in the previous case. All packets are pulled from the network using opportunistic local femto gateways that we strategically deploy for this experiment in the all wireless network of femtocells. Specifically, this one is an opportunistic local femto gateway, and this one. This is very useful in order to decrease the congestion in an all wireless network of femtocells. That is the addition of opportunistic local femto gateways. This allows the possibility of pulling from the network a higher rate, at a higher data rate that with the use of lower number of local femto gateways.
Okay, and that's it for the demo. Thanks very much for your kind attention. And if you're interested in knowing more about this demo or our routing scheme, the specific details, you can visit our wiki, which is iptechwiki.cttc.cat/routing. Or you can directly contact Jose Nunez or myself. You have the email addresses here. And if you're interested, we will also be present in, we have a booth in the Mobile World Congress 2013, so we can come and visit us and we will show you how the protocol works in a live way.